Hello students, in this video we will be talking about this op-amp, and first let me just give some sort of motivation why we are discussing about this particular topic, and later uh, we will continue this for the couple of videos after this. Okay, yeah. So now let me just consider a simple amplifier which is nothing but just a second. Yeah. So it's a CS amplifier, but the load that is being connected is an ideal current source load, and whatever the gain that we are getting out of the circuit is basically called as an intrinsic gain, just because uh, the gain of this entire configuration is purely dependent on the transistor alone. Okay, just because the load is an ideal, so it depends on the transistor, and we call this gain of this particular structure as an intrinsic gain. Okay, so whenever we talk about intrinsic gain, we are talking specifically about the gain contributed only from a single MOS transistor. Okay, and that could be expressed as something like I'll just write it as a sub int in order to mention that it's an intrinsic gain, and that is nothing but gm times r out with a negative sign. Okay, it's again it's an inverting amplifier. Now this r naught, we know that it could be expressed as 1 by lambda times id, and or it can also be defined in terms of an early voltage, which is defined as va or sometimes ve, okay, divided by id. So we have seen this particular quantity, that is this lambda, will have a unit which is in terms of volt inverse, and one can rewrite this particular lambda as something like lambda prime by L. Okay, so this is a much more important quantity, where lambda prime is a technology independent parameter, whereas lambda is specific to a particular parameter. So whatever we have written as lambda prime is something that is not specific to any technology, and it's a kind of technology independent parameter. So people generally try to mention in this way. Yeah. So that's all been said. The real reason for why I have done these many steps is to express this gain could be seen that it is actually proportional to the length, okay, the length of the MOS transistor that we have used. So in short, uh, when we go for a lower technology nodes like 180 or 65 nanometer technology, what happens is that the length of the channel reduces, and due to which the intrinsic gain that is produced by this single transistor becomes much smaller. Okay, so that is actually the motivation that we are talking about. So whenever we go for some deep sub micron CMOS technology, uh, it's only the like we get only a limited gain out of the circuit. So one has to exploit some different circuit techniques to derive a large gain out of this sub micron technologies. Okay, so and particularly in this video and in the following next couple of videos, we'll focus only on different circuit techniques in order to enhance the gain of the system. Okay, so but before I talk about the different techniques, so I'll just write it so that rather than speaking, I'll just mention. So we'll be exploiting some different circuit yeah. So we'll be exploring some different circuit techniques to enhance the or to enhance large gain, or to basically achieve large gain out of the circuit. Okay, to enhance the gain of the circuit. Yeah. So before I talk about those different circuit techniques that are used, I have to talk about something known as I have to specifically talk about some set of parameters which are specific to the op amps when they are in open loop configurations. Okay, so now these parameters which are the parameters of the open loop op amp basically defines the feedback circuit performances. Okay, so which means that these performance so these parameters that I am about to discuss is also termed as something known as performance parameter. And today our main focus will be on this parameters, and probably even today and tomorrow's class would be mainly focus on this performance parameters, and later we'll just move on to this different circuit techniques, okay, that is used to enhance the gain of the system. Now why are we really talking about or bother about this performance parameter, and what is this performance parameter? So I'll try to address each of these questions. So basically this performance parameter, or the parameters that we are talking as a performance parameter, is nothing but the parameters that belongs to open loop op amp circuit. Okay, so these are the parameters that belongs to open loop op amp, but in turn these parameters define the behavior or the performance of a closed loop system when these op amps are used in it. Okay, these open loop op amps are used in the closed loop configuration. Yeah, so hope that you're clear with what is this performance parameter. These are the parameters that belongs to open loop op amps, but these parameters in turn define the behavior or the performance of the closed loop system when such op amps are being used inside this closed loop system. Okay, yeah. So now what are these parameters, and what parameters we are actually going to discuss here? So in general there are some set of parameters that basically defines the behavior or the performance of the closed loop system. So they are, the very first quantity that we are going to discuss is about, or the parameter that we are going to address is this gain, and the second one is the small signal bandwidth. The third one is the large signal performance. My pen is not actually working out, so yeah. And the fourth one is the output swing. The fifth one is the linearity. There are a lot of performance parameter, but don't worry, we will not address everything, but one or two will be addressing as of now. All other remaining parameters will be discussed as and when it is when we discuss a particular topic. Okay. Yeah. So these are some of the parameters of the op amp, which basically defines the behavior of your closed loop system. Okay. Now among this set of parameters, we'll be focusing on probably the first two. Okay, I'll try to complete the first two, and the other parameters would be discussed as and when we discuss a specific topic, and probably the supply rejection would be discussed when we discuss about this BGR part. Okay, so in the case of a band gap reference, still we are yet to discuss about voltage regulators, and probably during that time we'll talk about this supply rejection over there. Okay, and even the noise will be addressed when we discuss about the noise part of our syllabus. Okay, so these are some of the topics, or these are some of the performance parameters that will be discussed as and when it is required, but specifically today we'll be addressing only the first two among this list. Okay, and the other parameters would be discussed during this op amp lecture itself. Okay, when we discuss about different circuit techniques. Yeah. So Now let me take the first one, that is the first performance parameter, which is the gain. Yeah. So let me try to draw a closed loop system that makes use of an op amp. Okay, so which is all familiar to you as of now, because we have discussed about this structures in the couple of lectures in the feedback circuit discussion. So yeah, so the configuration that is right now that has been drawn here is nothing but it's a non-inverting amplifier. Okay, so now let me try to discuss about how a kind of specification that has been defined on this closed loop system in turn defines the gain of this open loop system. Okay, so it is something like a kind of designer, or it's a kind of customer who just defines some sort of requirement, and these requirements are being converted in terms of a spec, and these spec in turn defines uh, the performance parameter of the open loop system. Okay, so basically it's a kind of or basically the specs are nothing but the the performance that a closed loop system has to attain. Okay, yeah, so hope that it is clear. Let me write the question. The circuit is basically designed for a nominal gain of 10. Okay, so now we know that this is a non-inverting amplifier, and uh, we also know that the closed loop gain, if at all, if I assume that this A, that is the open loop configuration A, is infinite. Okay, so it is under the assumption that if the gain or the open loop gain of this op amp is infinite, then one can write this to be equal to 1 upon beta, or it is nothing but 1 plus R2 divided by R1. Okay, yeah. So this is what we know, and they want this gain to be equal to a 10. Okay, but we know that in reality the open loop gain can never be equal to infinity. Okay, so the next, or basically the question is to determine the minimum value of this A for a gain error of 1%. Now what is this all about? Is that they basically a designer needs a kind of circuit. Okay, so which is the non-inverting amplifier configuration, and he needs a gain of 10, but he can have an error value of 1% among this, out of this 10. Okay, so which means that it can be like plus or minus 1% of the 10, or the gain of 10. Okay, so which means that it can have a value of AF, that is the closed loop gain, that can be either equal to 9.9, or it can be equal to, so within this range we want this gain to be there. Okay, so we don't want the gain to be out of this range, they want the range to be within this, to be located. Okay, now for that, what's supposed to be the value of this A is the question. Okay, what's supposed to be the minimum value of this open loop gain is the question. Okay, so now in order to solve this, let me first express the value of this V out expression. Okay, probably I have to bring this. So, from this V out expression, one could write that the value of this V out can be defined as something like, or basically let me write it at the input side. Okay. So, the quantity at this particular node value, or the voltage that I have across this particular node, or across the negative terminal of the op amp, can be returned in terms of V out, right. It's just the voltage division or simple voltage divider rule that could be applied on this network in order to compute the voltage at this particular node, and that voltage is taken as Vm, and the value of this Vm in terms of V out is defined as R2 divided by R1 plus R2. And we know that the op amp generally picks the differential input, which means that uh, it tries to differentiate between the Vin and the value of this Vm, and then amplifies by the gain of this particular op amp, which is the small letter a. So, right now one could express the value of this V out as the difference between this Vin and the value of Vm being multiplied by the gain of this op amp, okay, and that provides us the value of this V out. So, now that we will just try to plug in the value of this Vm and try to shuffle out some of the expressions towards the right, towards the left side, okay, so that we can, one could express into A, and on the right what we have is like V in times that of A, there is a gain that has been multiplied, so that V out by Vn, which is nothing but our feedback factor, okay. Yeah. Sorry, the feedback gain expression, and that is equal to A divided by 1 plus yeah. So, this is our very familiar expression where one could map the ratio of this R2 divided by R1 plus R2 is nothing but the factor beta, okay. Yeah. So, hope that you are clear with this. So, it is the same expression that we had been discussing right from the feedback video, okay. So, which can be expressed in terms of open loop gain and the feedback factor beta, and generally we call this A times beta as the loop gain. Yeah. So, hope that you are familiar with these quantities, and now let us try to simplify some of the expressions here. Let me try to pull out this factor beta out of this, or first of all let me try to pull out the factor of A out of this expression, so that uh, one would end up having a quantity that looks something like this, and again taking out this factor of beta away could be returned as something like 1 plus 1 by A beta, okay. It's a simple algebra that I have done. I've just tried to pull out this A beta term out of this expression, and then there are a few terms that cancels each other, and we end up having this quantity. And now there is something that we have to uh, think about this factor. If the value of A beta is much larger than the value of 1, then we know that this ratio or of 1 upon A beta would then be much smaller than the value of 1, okay. And using this binomial series, one could approximate this quantity of 1 plus 1 by A beta with the root of power like negative 1, okay, can be approximated with taking only the very first few terms, would end up having a result which is A beta, okay. So, hope that you are familiar with these kind of approximations based on the power series and stuffs, okay. I have just utilized those, and I have just considered only the first parameter, or the first parameter of this particular expansion, and I'm neglected all of the higher order terms just because the factor of 1 upon A beta is already much smaller than the value of 1, and one could neglect the other higher order terms out of this expansion. Okay, so due to which we end up having this feedback amplifier gain being defined something like this. Yeah. So now we know that ideally when the circuit has a kind of op amp whose gain is infinity, then we know that this AF would then be equal to 1 upon beta. Okay, and this is the expected value and this is what we wanted. Okay, but what is happening is that just because there is a finite amount of gain, we have this quantity not getting to a value of 0. Okay, but rather a value which is quite lesser than the value of 1, and in order to achieve a gain percentage of or basically to have a gain error of 1%, we want this quantity to be equal to 1%. So what it really means is that the gain is actually deviated out of this particular quantity by this particular expression, which is 1 upon a beta, and we call this expression of 1 upon a beta as the gain error, and we want to ensure that this gain error is not more than this 1%. Okay, we want to restrict this gain error to be lesser than 1%, and that is the question that we are being asked, or that is the spec that is being given to us. Okay, as a kind of designer. So if you want to have a gain error of 1%, then what's supposed to be the value of this open loop gain is the question. Yeah. So now from here one could write the requirement or the specification that this gain error we want to restrict to 1%, which means that it's supposed to be equal to 0.01, and in order to have this 0.01, we want some factor of a such that we can achieve this, and we already know that the nominal value or the nominal gain of this closed loop feedback is given as 10, and this nominal value can also be, or this particular feedback loop can also be rewritten in terms of 1 upon beta. Okay, whenever the a is at infinity. Okay, so due to which we have 1 upon beta to be equal to 10, and one could substitute over here, and due to which one could simply evaluate that the value of this a that is required would be equal to 1000. Okay, so this is the minimum open loop op amp gain that is required to have a gain error of 1%. Okay, so clearly you could see that a kind of specification that was given to this closed loop system has some sort of definition onto this open loop gain expression or open loop gain. Okay, so next we will just talk about the small signal bandwidth of this circuit. Okay, so before I really talk about the small signal bandwidth of the circuit, I want to emphasize on few of the terminologies. So I will talk about those, and then later we will just talk about how a particular specification turns out to define the small signal bandwidth of this open loop op amp configuration. Okay, so before that I just want to discuss about some of the terms that are involved in this particular expression. So let me begin with a simple RC network. We know that this simple RC network is nothing but it's a low pass filter. So probably we had been using this from even in the stability analysis videos we have discussed about this particular configuration, and whenever this RC network is operated with a step input, we know that the output will have a response with respect to time. The Vout can be expressed as a kind of exponentially varying signal, right? So it grows and then it reaches the final steady state. So one could visualize this Vout as a kind of two quantities. Okay, so Vout in time domain can be returned as 1 minus e to the power of t by tau. Okay, yeah. So it into the value of Vn. Okay, so this is the value of Vn here represents the amplitude of this particular signal, and for ease of our analysis, let us assume that the value of this Vn or the amplitude of this Vn is basically equal to 1 volt, so that I can drop this V in out of this expression. Okay, yeah, so it is something we need to consider over here. Okay, yeah, so now in this case there are two terms that are involved. The very first term, which is the value of 1, is known as the forced response. Okay, and the other term that is sitting is nothing but like the exponential to the power of t by tau is nothing but the natural response or the transient response. Now clearly when the value of t is small, okay, so at these points what happens is that we have something like e to the power of 0 quantity, and this quantity we know that it's a non-zero value. Okay, so the value of this is basically non-zero, and basically the v out is predominantly defined by this particular transient response, okay, or defined by this exponential term. But as the time grows, what happens is that you could see that this value, since because we have a t that is keep rising, and we also have one more term which is at the bottom, which is the tau term. Okay, now what is this tau and how it has been related to the circuit, that we have to discuss before I talk about the natural response getting died out after some time. Okay, now the tau is nothing but is the product of the resistance and the capacitance that we have across the node V out. Okay, and this basically defines the bandwidth of the circuit. So one could rewrite this expression in terms of a bandwidth, which is nothing but omega 3 dB frequency, as 1 by RC. So which means that this quantity can also be written as 1 upon tau. Okay, and as a kind of frequency response, if you could see the magnitude of the V out by V in is written, and here is the omega under the logarithmic scale, and initially the gain is at a value of 1, but after then I'm just talking about the 3 dB frequency. Say for example I have a bandwidth that defined over here as 3 dB or omega 3 dB here, and we know that the gain would be almost constant to this value, and at this particular frequency the gain would be degraded by a factor which is minus 3 dB, right, and the value that I would get, the actual value that I would get at this particular frequency would then be equal to 0.707. Okay, so you might be familiar with all these quantities. I'm not talking more about it. Yeah, so after this the gain starts reducing at a rate of minus 20 dB per decade. Yeah, so now there is something that we need to discuss, why this particular output is not having a step response as the input has it. Okay, so when I apply a step input, even the output do have to have the same sort of response, but rather we could see that the response has changed from a step to a kind of exponential graph. This is all purely because of the bandwidth of this particular circuit. So now what if I have a higher bandwidth? So what it really means is that if the factor tau is quite small, or if the omega 3 dB is quite larger, in such situation the output response will try to go to the final state very fast. Okay, just because sorry, just because it has more bandwidth to allow high frequency component. So in short, the step response has infinite frequencies in it. Okay, and if we could allow all the frequencies that are contained in this V in to the V out, then obviously we will get an output which is also looks similar to a kind of step output response. But just because we have a band limited circuit within this RC network, it is not possible for us to recreate the step response at the output. Okay, but rather what we get out of the circuit is basically this kind of behavior, slowly reaching to the final steady state. Okay, and so all of these factors are basically defined by this tau or this omega 3 dB. Now when I say that this factor omega 3 dB is being raised, this means that this particular omega 3 dB would then be shifted towards the right side. Okay, so we want this to be almost closer to infinity, and when we have such kind of circuit, then the circuit will have a bandwidth which is almost constant, okay, till it reaches some to this particular frequency. So it is we want this circuit to have a better bandwidth in order to have a step response at the output. Okay, so hope that you could be able to visualize how a bandwidth of the circuit defines the behavior of the output response for a step input. Okay, and this is more important for us to discuss, and that is the reason why we are talking about it. And here is the Vout expression that has been defined in terms of time domain, and one can also define the same quantity in terms of S domain as Vout by Vn in S domain as something like 1 upon 1 plus S tau, or I can also rewrite as something like 1 upon S by omega 3 dB. Okay. So both of these two quantities are same, and clearly you could see that this quantity which is V out by Vn is nothing but the transfer function of the RC network. Okay, yeah. So it is the bandwidth that is taken out of this transfer function. Okay, not out of the or basically the pole of this particular the pole frequency of my system defines the bandwidth of the circuit. Okay, so hope that you are clear with it. And right now let me just see how does this bandwidth uh, define some sort of requirement onto our circuit. And before I start doing that, there is one more point that I need to talk about over here. It's nothing but a term which is known as unity gain frequency. As I already said, it's the frequency at which the gain becomes 1, and probably I cannot use this circuit to talk about it just because I have assumed that the value of input itself is 1 and the gain of the circuit of an RC network is already 1. Okay, so we cannot discuss about that particular term over here, but rather what I do is that I'll just move on to a different circuit, uh, and we'll use some of the result to bring up the Vout expression out of this discussion of RC network. And later I will also talk about a term which is known as unity gain frequency for the configuration. Okay, yeah. So let me just bring back this circuit that I've drawn here. Yeah. So now let us assume that the op amp, that is the open loop op amp, has a single pole in this particular circuit. So what it means is that I have A of S, okay, which is defined as something like A naught, which is nothing but the DC gain, and whenever there is a pole, then I could write it as something like 1 by omega naught. Okay, so let us assume that instead of omega 3 dB, I just write it as omega naught here, okay, which is the bandwidth of the open loop system. And if you want, we can even write it in terms of tau as something like S tau naught. Okay, yeah. So there are too many ways by which one could rewrite. And let me also plot this as a kind of graph, the behavior of this response A of S in terms of frequency response magnitude plot as something like, so again those x axis is defined in terms of logarithmic scale, and we have a gain um, in terms of dB, let me put it. Okay, and so under DC conditions, what happens is that the gain stays almost constant, and when we reach a particular frequency of this, which is nothing but the 3 dB frequency of this open loop configuration, what happens is that the gain after crossing this, after reaching this omega naught will start degrading at a rate of minus 20 dB per decade. And let me use a piecewise approximation here rather than drawing this graph something like getting degraded at this omega 3 dB. I use this piecewise approximation lines. Okay, and after this, let us assume that the gain is degrading at a rate of minus 20 dB per decade. Yeah. So now, hope that it is clear. What I have drawn is only for the open loop configuration. I still have to talk about the closed loop configurations and its bandwidth part. Okay. Yeah. So now there is a particular parameter which is called as omega u. Okay, and that particular parameter is known as unity gain frequency, which is quite different from the transient frequency which we have discussed for a MOSFET. I hope that you remember those quantities that I have defined. Yeah, so it is a frequency. Let me write it, at which the gain becomes 1. Okay, so it can be either a closed loop gain or it can be even a open loop gain, but the gain is supposed to be equal to 1, and that is this particular quantity. Now, how would we evaluate this particular frequency omega u? Okay, so let me do it for both the cases, one for the open loop configuration as of now, and later after doing the closed loop transfer function, I will just try to redo the same uh, calculation of unity gain frequency. Okay, yeah. So now, since because we are worried about a particular frequency where omega, when omega is equal to omega u, what happens is that the gain of the system or the magnitude of this open loop system has become 1. Okay, so since because we have plotted yeah, and so magnitude can be written as something like a magnitude of a. Since because it's a DC quantity, we can remove those modulus, whereas we have to put a modulus for this 1 plus j omega by omega u by omega naught. Okay, yeah. So in the case of a denominator, we could see that there is a real term as well as an imaginary term. Okay, so whenever we try to make a modulus, we know how the formula that is generally used as something like square root of real square plus the imaginary part that is being squared. Okay, and now if we assume that this omega u is much larger, or the ratio of this omega u by omega naught is much larger than the value of 1, then one could approximate this magnitude. Okay, so again the magnitude of this open loop configuration will become a value of 1. Okay, so I can rewrite this 1, and this 1 could be approximated as something like a naught divided by omega u by omega naught. Okay, and from here one could quickly evaluate the value of this omega u to be equal to the product of the gain, which is the DC gain of the open loop configuration multiplied by the bandwidth of this particular circuit. Okay, so hope that this quantity is clear, and even when we try to evaluate the unity gain bandwidth of a closed loop system, we would end up having the same result. I will just show once we evaluate the closed loop response magnitude function. Yeah, so let me use a different color in order to talk about this. So we know that this transfer function V out. So again, right now, since because we have an S term that is sitting here, even this V out by V in can also be rewritten in terms of S domain. And I am just going to utilize those the results that we have used before. Okay, when we had the circuit and when we considered that this A was not having any pole in this particular open loop op amp. Okay, yeah. So let me. So it can be simply written as something like A of S divided by 1 plus a of s into beta, and we know what is the value of beta from the previous discussion, which is again can be returned as, let me just check it out, the factor beta that we have evaluated is equal to R2 divided by R1 plus R2. I will use that. Yeah. So there is a factor of this beta, and let us resubstitute this a of s expression with this quantity that has been uh, written here. So when we resubstitute, what happens is that becomes like a naught divided by 1 plus a naught, sorry, it is the other way around, 1 plus s by omega naught divided by 1 a naught to 1 plus s by omega naught into beta. And let us do some simple algebra here, trying to cancel out the, the terms that are common from both the denominator and the numerator. So one could cancel out these two terms, provided if we had already cross multiplied both these quantities. So after doing this cross multiplication and after cancelling out the common terms that are across the numerator and the denominator, we end up having a quantity which looks something like this. Okay, yeah. So now we will try to take out few of the terms that can be defined as a kind of DC quantity out of this expression. Okay, so clearly, if I could able to map out the terms of these that I have encircled with this yellow line, when I try to pull out as something like a naught divided by 1 plus a naught times that of beta, okay, then we would end up having a void which has been filled with a factor of 1 plus s divided by the whole quantity that has been taken out is being multiplied under the denominator of this s term. Okay, yeah. So this is what we have, and clearly you could see that the top term that we have, or the numerator term that we have here, is purely DC, which means that it is nothing but the DC gain of a closed loop system. So let me use a capital letter with a naught to represent the DC gain of the closed loop system divided by this 1 plus, again what we have here is a kind of same way however we had here, it's a DC gain of a open loop system divided by 1 plus s by omega naught. Okay, so where omega naught was the uh, frequency, or basically the 3 dB bandwidth of the open loop system, whereas here we also have a similar kind of notation. There is an s term, and under this s term we have, rather than omega naught, what we have is a kind of huge quantity, which is like omega naught that has been multiplied by a huge factor, which is 1 plus a naught times of beta. Okay, so let me write this quantity of omega naught into 1 plus a beta as something like omega c to represent that this is nothing but the bandwidth of the closed loop system. Okay, so clearly the bandwidth of the closed loop system has got enhanced, means that I have a very large value right now when compared to omega naught, and that value is being enhanced by this quantity, which is 1 plus a naught times that of beta. Okay, so clearly there is a certain improvement in the value of the or in the bandwidth of this closed loop system. And the other way around is that we have lost something when we paid when we are trying to gain a large bandwidth out of this closed loop system. And what is that? It's basically the gain. As you could be able to see that the gain that right now we have achieved, the DC gain of the closed loop system that we have attained is basically small. How small it is? It is small by this quantity. Okay, so we are not able to attain the value of this a naught, but rather it's been diminished by this quantity of 1 plus a naught times of beta, which is again a very large quantity here. Okay, so it is something like when we try to gain something, we have to lose something. Okay, yeah. So now let us try to use these data onto this frequency plot, okay, of the magnitude the frequency response plot for the magnitude. Okay, so in this case I have a small signal, I have this DC gain of a closed loop system, and depending on the factor of beta, I assume that the factor of beta is not equal to 1, and due to which I am just trying to draw a line assuming that this is my gain, and this gain will be almost constant till I reach the value of this or the bandwidth of my closed loop system, and this bandwidth would be mentioned somewhere here as omega c, which is quite higher than this previous value of omega naught, and this is because we are using a logarithmic scale. Even though it seems to be that omega naught is closer to omega c, it is still a bit away from omega naught and omega c. They are a bit apart from each other. Okay, yeah. So now, while trying to draw this graph of the magnitude plot, we assume that this a naught is constant till we reach this particular frequency omega c, and after then the gain starts degrading at a rate of minus 20 dB per decade. And clearly you could see that again this closed loop gain also intersects with the 0 dB line, or basically the unity gain. Okay, and we have a definition for this omega naught. Now let us recalculate this omega u in terms of or basically by using this closed loop system transfer function. Okay, so we have to attain the same result of what we have attained for the case when we used our open loop system. Okay, let us redo that. So let me write the conditions here. So when this omega is equal to omega u, the magnitude of this closed loop transfer function at that particular frequency supposed to be equal to 1. Okay, so we'll just write this factor of or the value of 1 over here, and that is nothing but it is written as 1 plus s by, or basically j omega u by omega c here. Okay, so this is different, and that has to be taken under the square root, and then it has to be done. Okay, so I'll just put a modulus here, and since because there is a real term and an imaginary term, one could rewrite this quantity as something like a naught divided by square root of real part square times the imaginary part square, and let us assume that again the factor of omega u by omega c is much larger than the value of 1, and due to which one could approximate this quantity is equal to omega u by omega c here. Okay, yeah. So now again from here one could write this omega u is equal to a naught times that of omega c, but we know that this a naught can also be rewritten in terms of the open loop DC gain, which is nothing but a naught divided by 1 plus a naught times that of beta, and even this omega u can also be rewritten omega c can also be rewritten in terms of the bandwidth of open loop system, which is nothing but omega naught into 1 plus a naught times that of beta. So clearly you could see that these two quantities would then cancel, and we get a value of this omega u, which is nothing but the product of open loop gain times that of the feedback factor. Okay, so we have attained the same result that we had before. Sorry, it is not beta, it is omega naught. Yeah, so we got the same kind of result both using the open loop as well as the closed loop configurations. Okay, yeah. So now we will come to the business about the discussion of a problem here, and I still have to tell you or teach you how a particular specification can define the bandwidth of this particular circuit. Okay, just give me a second. So let us assume the same circuit that I have used for this discussion, the non-inverting amplifier configuration, but the question for this is to attain this. Sorry. So let me try to increase the font size. Yeah. So let me also collect our op amp that has been drawn. Maybe so copy it and then try to, yeah, yeah. So in this case, we have been asked to calculate the time that is required for a step input, okay, uh, that has been applied at the input. We want an output to reach what time it requires for an output to reach its final value, okay. So that is what the first question, and later you have been asked to calculate what is the factor fu. So fu is nothing but the unity gain bandwidth, and that must be satisfied by the op amp to have a nominal gain of 1 plus R1 by R2, which is nothing but the 1 upon beta factor that's supposed to be equal to 10, and also we want the settling time to be less than 5 nanosecond, okay. So if you want the settling time to be less than 5 nanosecond, what's supposed to be the unity gain frequency of this open loop op amp is the question, okay. So let me just put everything into a perspective. Now first let me try to express this V out in terms of time domain, okay. So based on all our previous discussion, I hope that you can clearly you are now more equipped with how we got this expression. So I'm just writing the expression directly. So I'm just writing this V out in time domain as our normal case. There will be a kind of force response minus there is a kind of exponential term which is the natural response divided by a factor tau c, okay. So now here tau c is nothing but the time constant of the closed loop system, okay. It's a quantity that has been related to the closed loop system, okay, just because we are talking about the V out of this closed loop system here, and I have it here, and obviously there is a gain from input to the output, okay. So one has to take care of that, and that gain is nothing but our nominal gain quantity, okay. So which is 1 plus R1 by R2, which is nothing but the 1 upon beta factor, and we know that this quantity is basically the value of 1 here, okay. Yeah. So now graphically what there has been asked and what has been told in the first two statements here is that we know that for a step input, okay, let us assume that the magnitude of this is equal to 1, okay, just for the ease of purpose, and we know that the output will not have the same similar shape or the magnified version of the same similar step response, but just because of the limited bandwidth of this particular open loop configuration, what would happen is that there will be a kind of exponential growth in our output response, okay. So the output would then change or would then grow something like this, and then it tries to reach the final state, okay, and the value of this final state is basically, okay, let me write this expression of Vf, and let me write the y-axis as well as the x-axis of this graph. Yeah, so finally it reaches a final steady state, okay, and that final steady state is the quantity that happens or that would be equal to 10 when this natural response is completely died out, okay. So when can this e to the power t by tau c can die out is only when the time t goes all the way to infinity. We know that e to the power minus infinity is basically equal to 0, right. So we want this time to run a very long period in order to make this natural response to completely die out of this particular uh, response, okay. But depending on the bandwidth or depending on this factor tau c, we can ensure that the output voltage can reach the final state uh, of a particular precision, okay. So that can be defined by working on this bandwidth of this closed loop system, okay. So what it really means is that let me try to read out the first question over here. So the first question basically asks about how much time it is required to reach 1% of its final value. So what it really means is that we are looking for a time, okay, where at this particular time we have reached 99% of its final value, okay. So or 0.99 times that of the v final value. Now you might wonder what is this v final basically. Now v final is nothing but it's a v out when t is 10 to infinity, okay. So which means that it is equal to this quantity, okay. And I have assumed here that the value of this input magnitude of the SIP input is equal to 1 volt, okay, and that's the reason why I have not multiplied with Vm. Otherwise, if I replace this 1 volt with Vm, then it's a magnified version of this Vm onto the output, okay. Yeah. So now we are required to compute this particular time t. Okay. Now in order to have this, so and this is nothing but our settling time, and this is the quantity that we have defined here as our settling time. And the second part of the question is basically uh, is asking that the settling time needs to be less than 5 nanosecond. Now if this has to be less than 5 nanosecond, then obviously one has to worry about the omega u factor, okay, or in short one has to think about the omega c factor, okay. So this is how the link grows on. So we have to think in that perspective, okay. So how a settling time that was being defined for a closed loop requirement as is in turn is defining the omega u factor or the omega naught factor, sorry, yeah, of this open loop configuration or the bandwidth of the open loop configuration, and that is what we are trying to connect through these examples, okay. So let us try to work out this example. So when this time t, and let me write it as ts here, okay, and we are going to assume that this ts is the time that is required for us to for this v out to reach 99% of its final value, and the final value is given by this expression, okay. Yeah, so hope that you are clear with this. And when the time is t is equal to ts, then one can write this v out at ts is 0.99 times that of the final value vf, and I'm just trying to resubstitute this expression of this v out, okay. So I'm just resubstituting this expression on towards the left side or on towards the right side, which is 1 plus r2 divided, sorry, r1 divided by r2 into the exponential part ts by tau c, okay. Yeah, so now there are a few common terms that could be cancelled out just because when we know that this vf is also written as 1 plus r1 divided by r2. So from both these quantities one could cancel out some of the common terms. So in this case the 1 plus r1 by r2 is a common term, and we ended up having 0.99 to be equal to 1 minus e to the power of ts by tau c, okay. Yeah, so we have this quantity, uh, and this value would be equal to 0.01, and over to the right side, so towards the left side we have ts by tau c, and again we have a negative sign here, so one could rewrite, and taking ln on both the sides we would end up having this ts to be equal to tau c into ln of 100, okay. Yeah, and this is just a value, right. So if I try to calculate what is the value of this ln of 100, we would end up having an approximate value of 4.6 times that of tau c, okay. And since because we want this ts, which is the settling time, to be lesser than 5 nanosecond, so we want this quantity towards the right side to be something like this. Okay, so this is the definition that I have written. So hope that you are clear with this. So from here one could write the value of tau c in terms of unit of time, okay, as so it is just a simple division of 5 nanosecond divided by 4.6 will give us the value of tau c, or the closed loop time constant. Okay, yeah. So now one could rewrite this tau c in terms of just a second. Yeah, I somehow have to relate this. Let me rewrite in terms of omega c, so that we are familiar with those. So I will just rewrite this tau c in terms of omega c as something like 0.09 nanosecond, and this omega c can also be returned in terms of omega naught as 1 plus a naught times that of beta, right? Yeah, and if at all, if I assume that this particular factor is quite larger than the value of 1, and I could write it as omega naught a naught times that of beta to be equal to 0.09 nanosecond. Okay, yeah. So from here the nominal value of the gain that is expected out of the circuit is basically 10. So which means that the DC gain of this closed loop system can be a value that is equal to 1 upon beta, and that's supposed to be equal to 10. So from here we have a value which is equal to 10 and omega naught a naught that is equal to this quantity. And now we know that this product of omega naught times that of a naught is nothing but it's a quantity that is equal to omega u. Okay. So this quantity is nothing but the unity gain frequency term, and now it is this value is what is being asked in the second part of the question. So this omega u is nothing but it's 10 divided by 1.09 nanosecond, and if you try to evaluate this value, I guess you would get I don't have the value, I guess. Yeah, I guess it is closer to a value of 9.21 or 1. Yeah, so it is in gigaradians per second. Yeah, so clearly you could see that the definition of or the requirement of a settling time to be less than 5 nanosecond has imposed some sort of unity gain bandwidth of the open loop configuration, or the open loop parameters unity gain bandwidth. Okay, so this is how we could see that basically the specification in turn defines a particular parameter of the open loop configuration, and we have discussed today two among those parameters. The first one being the gain. We saw how a gain error defines the open loop gain, and in the second example we saw how a settling time requirement has imposed a kind of unity gain bandwidth onto this open loop configuration. Okay, so let me complete today. Let me stop over here today, and in the next class we'll talk about different circuit techniques that is basically used to enhance the gain of this particular system. Okay, yeah, thank you.